Welcome back. As I already told you that an image is a specialized signal, where the speciality is that an image is a two-dimensional signal. Now, for the sake of understanding, the two dimensions in an image can be considered as the height and let's say the width of the image. Or more technically speaking, the two dimensions in an image are spatial dimensions. Mathematically speaking, an image is a two-dimensional function f of xy where x and y are spatial coordinates. Now in case of black and white, or what I will refer to as grayscale images for the rest of this course, now in case of black and white or grayscale images, the function f is single valued and that value represents the intensity or the gray level of the image. In case of colored images, this function f is multi-valued. Now images are a representation of an analog world. The images are basically analog signals. And in order to process our images through our digital systems, we need to digitize the images. Now, as on the previous slide or earlier, this image of this beautiful woman that I've been using is not just a mere coincidence. In fact, this image, known as Lena, is a standard test image that has been used in image processing since 1973. This image is of a Swedish model whose name was Lena Forsén. In 2015, Lena Forsén was the guest of honor at the banquet of IEEE International Conference in Image Processing held in Quebec City in Canada. I too had the privilege, or let's say the honor, of presenting my research work titled Multivariate Texture Discrimination Using Principal Geodesic Classifier at the same conference. And I think I consider myself lucky in a way that I met her and saw face to face this beautiful woman, Lena, whose image has been used as a standard test image in image processing since a very long time. Further, if any one of you is further interested in this research work that I presented at that said conference, feel free to contact me further in this regard. An image is represented by a function f of x or y, where x and y are discrete coordinates. This function f of xy can be expressed as a matrix, as is shown over here. The matrix contains m rows and n columns. Now, each of the elements of this matrix, for instance, let's say this first element, f of 0, 0, or possibly this last element, f of m minus 1, n minus 1, each of these elements of this matrix are called a pixel or a picture element. Now, in case of a black and white or a grayscale image, the pixel value represents the intensity. Now, and in case of a colored image, the pixel value represents the color intensity. Now, as we saw earlier also, an image is basically an analog signal, and in order to express it in a digital computer or process it in a digital system, we need to digitize the image. Digitization, we have already seen, involves two processes. There is sampling and there is quantization. And now the analog picture, once it has gone through the process of sampling and quantization, becomes a digital picture. However, this digital picture, which is a result of the process of digitization, is in fact an approximation of the real image. For black and white or grayscale images, there is one sample or one value for each pixel, and that one value is the intensity. For colored images, there are 3 samples or 3 values for each pixel. Now, there can be 4 samples or 4 values per pixel as well, where the 4th value can be the opacity. Opacity is a measure of transparency of an image or the transparency of an object inside the image. Okay, now that we understand what a digital image is, let's look at what digital image processing truly entails. Digital image processing focuses on two major tasks. Number one, it is the improvement of pictorial information for human interpretation. And secondly, it entails processing of image data for storage, transmission, and representation for autonomous machine perception. Image processing leads or overlaps with fields such as image analysis and computer vision. The algorithms, tools, and techniques in digital image processing can further be divided into low-level processing, mid-level processing, and high-level processing, depending upon the complexity of the processing system. So now, in a low-level process, the input to the program or the algorithm is an image, and the output from the program or the algorithm is also an image. A possible example of a low-level image processing system is, let's say, noise removal from the image. Now, in a mid-level processing system, the input to the system is an image. However, the output now is certain features or attributes or characteristics of the image. One possible example could be object recognition. This can, let's say, be better understood that, for instance, face detection. And an image is input to a certain algorithm, and that algorithm or program at the output detects the faces from that image and presents those faces. So object recognition is one example of a mid-level digital image processing system. Then in a high-level digital image processing system, the input to the system, which can be a program, an algorithm, or whatever, the input to that system are features or attributes or characteristics of the image, and the output is a certain understanding or a certain action. An example of this is autonomous navigation, which can be best understood by the working of Google's self-driving car. So there's Google's self-driving car, which takes in the front scene as the input image, and then based on certain attributes that it extracts from that input image, it makes a decision that as to whether that car is going to stop or that car is going to take a right or, let's say, a left turn. Now that we have looked at digital image processing broadly, we're now going to go through certain steps which take place in a digital image processing system. Now, it's possible that a certain system, in a certain system, all these steps occur. However, at other times, only few of these steps take place. The first step, of course, naturally is image acquisition, which is that our digital image processing system acquires the input image. The second is pre-processing, which is, let's say, that once we have acquired the image of interest, we improve its quality by filtering. We could possibly remove noise from it. Then the third step is segmentation. We partition our input image into smaller parts for further processing. The fourth step is description of feature selection. By this we mean that from that input image, we extract certain attributes or characteristics of interest, which will then help us in further processing. Now, in order to understand this, I could possibly give you an example of one of my master thesis students. She's working on automatic facial expression recognition. So what she does is that she gives an image as input to her processing system or her algorithm. So from that input image, as a first step, the face is detected. Then after that face has been detected, certain attributes from the detected face are then computed. For instance, let's say what the width of the smile or width of the mouth is, or if that face has a certain frown or it doesn't have a certain frown. So similar characteristics are then extracted from the detected face, because the ultimate goal is that the system wants to automatically determine that what expression that face has, if that face has a happy expression or a sad expression or a frightened expression. Then the final or the fifth step in digital image processing is recognition and interpretation. Now, continuing on this automatic facial expression recognition example, the last step would be that once those useful attributes, which I just told you, that if a frown is there or not, or what the width of the jaw is, from these extracted attributes or characteristics, it is recognized that what that expression is. So based on these attributes, a decision is made that, let's say, that face has a happy expression. And then, of course, further, once we have recognized what we wanted to recognize, then we further interpret it for understanding the better meaning, or for or whatever the demand of our application is. Moving on, Theodore Roosevelt, a former US president, said that in order to understand the future better, it is important to first understand history. So, briefly looking into the history of digital image processing I believe, will be fruitful for you. So digital image processing began somewhere in early 1920s. One of the first application of digital image processing was in the newspaper industry. The Bartland cable system were these submarine cables between London and New York that were used for transmitting these images for newspapers. In 1921, the Bartland cable system was using 5 gray levels for transmitting the black and white picture, and it would take close to 3 hours for the transmission of the picture. Then towards the end of 1920s, they were using 15 gray levels. Now the pictures, they were coded by using these, the pictures were coded, and then they were transferred through these submarine cables, and then were reconstructed at the receiving end on a telegraph printer. From mid to late 1920s, improvements to the Bartland system resulted in higher quality images. New reproduction processes based on photographic techniques led to an improvement in quality, and as I told you earlier, that by the end of 1920s, up to 15 gray levels were used in the production of digital images. In the 1960s, improvements in computers and computing technology and the start of the space race between the former USSR and the USA led to a massive increase in the work in digital image processing. Over here on the right is a picture of the moon that was taken by the Ranger 7 space probe minutes before it landed on the moon. Ranger 7 was a space probe of USA, which for the first time successfully sent back photos of the moon to the Earth. Further digital image processing techniques were developed and widely used in space missions such as the Apollo landings. Apollo landing towards the end of late 60s was the first time human actually landed on the moon. In the 1970s, digital image processing became even more important as it found application in the medical field. In the year 1979, Sir Godfrey Hounsfield and Professor Ellen Cormack shared the Nobel Prize in Medicine for the invention of tomography, which is the technique behind CT scan. From the 1980s till today, the use of digital image processing techniques, their development, their analysis, their application is only becoming increasingly more important. Today, digital image processing techniques and their application are prevalent in all walks of life, and this is what renders digital image processing a very important subfield or sub-area in electrical engineering, computer engineering, and even other engineering disciplines.